All right, I think it's 5 past, so we can start. So welcome everybody to this week's Autonomy Talk. Today is a pleasure to have with us Annie Xie. So Annie Xie is a PhD candidate in computer science at Stanford University. Before Stanford, she graduated with a Bachelor of Science degree in electrical engineering and computer science from the University of California, Berkeley. Her research focuses on developing reinforcement learning algorithms that enable robotic systems to learn with minimal human supervision. Annie is a recipient of the National Science Foundation Graduate Research Fellowship and the Best Paper Award at CORE 2020. So I think with no further ado, the stage is yours. We're all looking forward to hearing what you're gonna tell us.
Yeah, thank you so much for the introduction. Yeah, so I guess I'll just talk a little bit more about myself before I start. I am a 4th year PhD student and at Stanford, advised by Chelsea Finn. And throughout my PhD, I've been really interested in reinforcement learning algorithms for robotic systems. And as you've mentioned, I've been interested in how we can develop these robotic systems that can autonomously and continuously learn in the world, requiring as little human supervision as possible. And so for me, one of the appeals of studying AI and reinforcement learning through robots is seeing the many possible ways in which one can interact with the physical world and and how this world shapes what's actually learned. But of course, one challenge of learning in the physical world is that it's really hard to exactly model during training time. And so ideally, we'd like to train our robots either within a realistic simulation of the world or from offline data that we collect in it, or even with online reinforcement learning. But a lot of the times there are these small differences between the environment that the robot trains in and the environment that we want to deploy the robot in. And so, for example, let's say we've trained a policy for this robotic arm to stack a bunch of blocks in this particular configuration on top of the table. If, for example, one of the table legs comes loose, the table becomes a bit wobbly, and the policy that we've trained could fail under this relatively small change. And as another example, sometimes we might want robots to complete a task differently. For example, one user might want the configuration that we see on the left, but a different user might prefer the configuration that we see on the right. And while I don't expect the agent to kind of immediately produce a policy for this task on the right, having only learned the one on the left, it would be great if it could transfer what it's learned from the training task to solve this one faster, since I would consider them pretty similar tasks. And through these two examples, I'm hoping to highlight, I guess, how the world, which I would include the varying conditions, as well as the different users that might interact with the robot. This world is really big and extremely complex. And so this makes it really difficult to sort of correctly and to completely model during training time. And so my proposal to this problem isn't to try to capture all of the possible variations and the possible conditions and the preferences of people, but instead to try to design systems that can continuously adapt and continuously learn in this very kind of complicated and dynamic world. And so in short, I'm going to talk about how we can equip agents with the mechanisms necessary to kind of allow them to be learning constantly on their own. And so how can we do this? I guess I've been hinting at this already, but I think a pretty good candidate solution for this problem is reinforcement learning. So RL algorithms, especially on policy ones, have the ability to kind of continuously adapt to the environment that it's in, even if it is changing. And they also have the ability to leverage the data that's collected from past policies, and this makes it more efficient, especially when learning new tasks. But at the same time, they can fail to kind of quickly adapt to really big and extreme shifts without giving them additional mechanisms. And a lot of these algorithms also require resets to the environment to kind of create episodic learning for the agent, which prevents, I guess, the ability to do autonomous and continuous learning. And so this talk focuses on how we can make RL more suitable for continual learning by trying to address these 2 points. So as I've said, RL can struggle to adapt to extreme shifts in the continual learning setting, but these shifts can occur in both the task definition as well as the environment itself. And so to address this, I'll talk about an algorithm that's able to kind of learn new tasks a little bit more efficiently by reusing data collected from prior tasks. Then I'll talk about how RL agents how RL agents can try to learn under highly non-stationary conditions. And finally, we want to, I guess, enable these agents to operate as autonomously as possible, which means without environment resets. And I'll talk about an algorithm that explicitly detects and avoids states in the environment that might, I guess, like hinder this progress. Cool. So in this first problem, we're interested in kind of learning robot policies for a sequence of tasks. And this problem has been studied pretty extensively in the supervised learning setup, and also to some degree in the reinforcement learning setup. And so a lot of the existing work in the space has been concerned with catastrophic forgetting, which basically evaluates how well a learner that's given a finite amount of memory and parameters can perform on previously solved tasks. And so in our setup, we're kind of concerned with a slightly different aspect of lifelong learning, which is forward transfer. And so at the same time, other work like meta learning has kind of also studied the similar problem of transferring to new tasks. But meta learning algorithms kind of in their like standard formulation require access to a large set of tasks during meta training, which isn't always feasible in the physical world. And so here in this work, we're trying to develop a solution based on reusing data from previous tasks. And so in this setup, we're specifically allowing the agent to kind of retain all of the previous experiences that's collected in the past, which we don't think is particularly unreasonable since storing data is usually pretty low cost. And so another kind of assumption in this problem setting that we make is that the state and action spaces are shared between all of the tasks, and only the transition dynamics and the reward function are varying across tasks. And so from this, we also kind of define the problem so that the agent can only advance to the next task once it finishes the current one, and it never revisits any of the previous tasks. Another sort of assumption is that we kind of allow the agent the ability to evaluate basically all of the rewards from every state action pair for the task it's currently solving. And so this reward function, while we kind of give it the oracle reward in our work, can often in practice be recovered either through demonstrations of the task or through kind of examples of successful states. And we can kind of try to recover this reward function through inverse reinforcement learning. But essentially, we're giving the agent the ability to kind of relabel the rewards of the state action pairs that were visited in the previous tasks. Okay, so next I'll outline our solution to this problem, which basically alternates between an offline pre-training phase and an online improvement phase for every new task that comes in. And so during the offline phase, we'll restore the replay buffer. The replay buffer is collected in the previous tasks, and then we'll relabel each transition with the reward function for the current task. And then finally, we'll pre-train the agent on this data, just running kind of any offline reinforcement learning algorithm. And then during the online phase, we'll try to kind of further improve the agent's policy by collecting online data. And here in this phase, we'll also try to reuse kind of the prior data. And so, of course, kind of naively, one solution is to just kind of train all of the old and all of the new data uniformly. But as we'd expect, this wouldn't be very effective. Instead, we'll kind of try to just find the most relevant previous experiences and reweigh those old transitions based on how likely they are under the current task's dynamics versus a different task's dynamics. And so kind of this importance weight that I just described can be kind of decomposed into these two terms here. And the first term, which is underlined in green, basically says, given a transition sample, how likely is it to be from the current task versus a previous one? And so here to kind of estimate this importance or this particular ratio, we follow kind of prior work on domain adaptation and estimate this ratio by training a binary classifier on the transitions using kind of the standard binary cross entropy loss. And we can kind of further transform this ratio by thresholding it. So instead of reweighing samples, which in the past has been found to be quite unstable, we're essentially just filtering out the unlikely samples and keeping the most relevant ones. And the second term here, underlined in yellow, we can actually estimate through kind of the size of the data sets. And this term basically decreases the weight of the old samples as we collect more new samples in the current task. And so that's pretty much it. To summarize, basically for every new task that comes in, our method will first try to use the previously collected data for offline pre-training, and then we'll filter out the irrelevant experiences and combine them with the new online data in fine-tuning. So we evaluate our solution in first a simulated key insertion task. So here we designed a group of these tasks, essentially by varying the box placements, as well as whether they're kind of placed flat or vertically, so that there's more kind of heterogeneity. And we also varied the size of the key and the initial orientation of the key with respect to the box. And then we also looked at the second domain where that we have this kind of three-fingered robot that has to rotate the valve to a specific goal orientation. And here we varied the feedback gain as well as the friction coefficient, the shape of the valve, and the target orientation of the valve across the different tasks. So this plot, this first plot visualizes the performance of our method as well as a few different methods on a sequence of key insertion tasks. And so here we see that our method on average outperforms the baselines, and these baselines include kind of just learning each task from scratch. It also includes progressive neural networks, which is one of the existing kind of lifelong learning algorithms. And this method called DARK, which is more similar to our method in that it tries to reuse, I guess, old experiences and reweighing them through a different importance weight. And I guess what's notable here is that on some tasks, for example, on task number 10 and task number 16, our method is the only one that kind of even learns to solve the task at all. And we see a similar trend on the valve rotation tasks. And so on these, the progressive nets baseline achieves similar performance. And this baseline kind of it essentially transfers the previously learned representations across different tasks, as opposed to transferring kind of the raw transition samples, which is done by our method and the DARK baseline. And so likely in this sequence of tasks, these representations learned by progressive nets may be transferring a little bit better compared to the key insertion tasks. But I guess the main takeaway here is that in both of these domains, our method achieves over 80% success and also improves upon the prior methods. So far we've reused the experiences collected by the learner. In this particular experiment, we asked, can we reuse data collected by other policies? And so here we applied our method, but on data that's collected by just a random policy that samples random actions uniformly. And we collect this data in the prior tasks, but we find that our method, which is in orange, is still able to kind of outperform learning the task from scratch. And this kind of suggests that our algorithms isn't super sensitive to the composition of the data set and is still able to kind of learn from this data collected randomly in the previous tasks. In our next experiment, we want to study whether this data set of prior experiences can be reduced, since keeping around all of the previous collected data can require a lot of storage and computation as the number of tasks grows. And so here we essentially just uniformly sample 10% of kind of the old data. And this procedure is also known as reservoir sampling. And we find that our method's performance, which again is in orange, is similar to just training on the full data set, which is in blue. And so next, we evaluated our system on a Franca robot on a sequence of different tasks, which includes diverse setups like bottle capping and block insertion. And so this plot essentially shows the distance to the goal across the 9 different tasks that we trained in. And overall, our method learns faster and finds a better solution than if we were to kind of train the robot from scratch in each of those 9 tasks. And we see that it gets within around, I guess, like 0.75 centimeters of the goal compared to, I guess, the 1.83 achieved by learning from scratch. And so to summarize this part, we found that leveraging the relevant prior data gives us better solutions and also uses significantly fewer training examples. Specifically, we found around a 2 times reduction in our experiments. And through the ablations, we also saw that our method is pretty robust to the composition as well as the size of the data set of prior experiences, which are pretty neat properties in the context of continual learning, which kind of involves like a lot of data, but not necessarily not necessarily high quality data all the time. And so far we've talked about how to adapt to new task definitions quickly, but we still see that existing RL algorithms struggle to adapt to changes, especially in the conditions of the environment. And so, for example, imagine a legged robot that's trying to navigate extremely varied terrains, such as grass, to sand, and to gravel. And so under this kind of non-stationarity, we found that RL algorithms, even on-policy ones, can kind of struggle to keep up with the constant changes in the environment. And so one way to model this kind of non-stationarity is with a Markov decision process that has underlying parameters that vary over time. And so I guess other kind of valid formulations of this include the POMDP, which can in principle model non-stationarity as part of its underlying state. But it could also kind of be too general, especially if we're considering changes that occur over a longer time scale. There's also the kind of Bayes adaptive MDP and the hidden parameter MDP, which both consider a set of parameters that underlie the MDP that aren't observed, but they assume that these parameters are fixed. So these formulations don't fit the setting particularly well either. And so kind of motivated by these formulations, we introduced what we call the dynamic parameter MDP. Essentially, this MDP is equipped with a set of task parameters that essentially define that parameterize the dynamics and the reward function. And these task parameters can kind of be thought of as physical parameters, for example, like the type of terrain that the robot is walking on, or the mass of a payload. Maybe this mass is kind of varying over time, or for example, like the direction of the wind force that's acting against the robot. And so this model essentially is a sequence. You could view it as a sequence of tasks where the parameters for each are determined by this kind of unknown prior POZ prime given Z. But here we make kind of two important assumptions in our model. And the first is that the agent gets to observe when the task parameters shift, which we call kind of the task boundaries. And to simplify the notation in this work, we essentially assume that these task boundaries coincide with the episode boundaries of training. And we also assume that these shifts are predictable to some degree. So one example is how weather conditions can often change predictably. And our method will try to leverage whatever pattern there is to try to anticipate future changes. Great, so now that we formulate the problem, the objective we kind of propose to minimize can be derived from this like framework called reinforcement learning as inference, but it's essentially outlined here in the bottom two lines. But what's nice about this objective is that it basically decomposes into two very intuitive components. And so the first component here, highlighted in blue, essentially corresponds to variational inference in a sequential latent variable model, where the observations are the agent's trajectories and the latent variables are the hidden task parameters, the sequences of Z's. And the second component corresponds to performing maximum entropy reinforcement learning, where the policy is conditioned on the inferred task parameters. And so together we can view this objective as performing essentially joint representation learning of the environment, followed by reinforcement learning with this representation. And to optimize this objective, we propose our algorithm, which we call lifelong latent actor-critic, or LILAC for short. And essentially, in LILAC, we to implement this, we introduced an inference network that tries to infer a distribution over the task parameters given the observed trajectory, as well as a decoder network that reconstructs this trajectory. And since the prior P of Z prime given Z is unknown, we also try to learn it with a neural network on top of this representation. And all these components are built on top of the soft actor-critic algorithm, which takes in the task parameters from the inference network and conditions both the policy and the critic on it. Then essentially at test time, when the agent acts in the environment during a new episode or a new task, we first infer the latent task parameters from the previous episode. And with this learned prior, we can predict the next set of parameters and pass that to the policy. Cool. And we next evaluate our algorithm. To do this evaluation, we designed a few different environments that sort of exist, that have the non-stationarity that we might kind of find in more realistic settings. For example, we might want a robot to track a moving goal, or to kind of move against different wind forces, or to carry different payloads. And in our experiments, we also kind of we compare to a few different existing algorithms, sort of representative of various reinforcement learning paradigms. First, we compare to just soft actor-critic, which is representative of standard off-policy RL, and this method called SLAC, which is intended to solve POM-DPs, and PPO, which is chosen to be representative of on-policy RL algorithms. And so overall, in kind of these various domains, we find that LILAC, our method, maintains more successful behavior in each of these in each setting. And unlike the other methods, kind of LILAC is able to do this by proactively modeling the changing task parameters and anticipating these changes in the environment. As I guess next, we kind of investigated LILAC across different kind of ablative experiments. The first here is to see whether our method can kind of handle environments with different rates of non-stationarity. And what's nice is that we find that LILAC does perform kind of pretty much similarly across the different rates, but also in the case where the environment is stationary, which is kind of the dotted black line. So here the environment doesn't change at all. We see that LILAC is able to kind of recover the same performance as standard RL. Then we studied a setting where the environment is shifting at every time step, which basically breaks one of the assumptions of the dynamic parameter MDP. But we still find that LILAC learns more successfully than the baseline, especially when we additionally condition the policy on the episode time step. And finally, we see that LILAC can even model environments that have kind of these like continuously extrapolating shifts and handle new task parameters pretty well. Though we do see kind of some degradation as these task parameters kind of diverge from the distribution that it saw during training. And so aside from kind of the naturally occurring changes in the environment, another way that non-stationarity can arise is from other agents and kind of their changing policies. Since these other agents' policies aren't usually observed, basically the environment can be viewed as non-stationary from the perspective of the learning agent or the ego agent. And we found that by using by applying LILAC, we can model the changing intentions of other agents and allow the agent on the left, this is not repeating, the agent on the left to learn a policy to play air hockey with the agent on the right. Great. So to summarize, this algorithm that we introduced tries to handle the sort of lifelong continual non-stationarity by modeling and anticipating the changing latent parameters of the environment. Our algorithm is also robust to kind of continuously shifting environments, so environments that shift at every time step, as well as environments that have extrapolating task parameters. Great. So next, I'll kind of be talking about something a little bit different, but I guess to motivate this a little bit, besides non-stationarity, there's another property of the world that kind of prevents this like continual autonomy that we'd like, which is kind of the irreversibility of some states in the world. And so ideally, robots should be able to learn completely unattended, but these irreversible states kind of challenge this goal since they do require kind of this external intervention to recover from these states. So kind of as a concrete example, let's say we have a legged robot. This legged robot might flip over, or if we have a robotic arm that's trying to kind of manipulate some objects, this arm could knock kind of an important object somewhere outside of its this reach. And since resets can be really hard to automate in kind of more real world situations, they do require a little bit more monitoring. And so in the worst case, these resets might look like a human that's kind of constantly supervising the robot and resetting the environment when necessary. So for example, when the agent enters an irreversible state, and these resets essentially make continuous learning really difficult. But of course, realistically, it's impossible to kind of anticipate all the irreversible states of the world, and inevitably robots will kind of encounter some of these states. But kind of the goal of this work is to try to be less dependent on these interventions. And to do so, we kind of try to design essentially agents that can detect and hopefully avoid these irreversible states by kind of, I guess, especially the states that like resemble the ones that they've seen before. And hopefully this will allow the agents to only request these interventions when actually needed. And so concretely, in our setup, we define irreversible states to be states that belong to a different strongly connected component than the initial and the goal states. And in our setup, we allow the agent to request the reset interventions, but we also allow the agent to query reversibility labels during training. And so these labels are essentially the binary labels for each state, indicating whether the state is reversible or not. And so we do assume there's like, based on like this ground truth definition of irreversibility, where there exists an oracle, which could be kind of in practice, in the worst case, could be a human oracle, but there exists this oracle function that that returns whether a particular state is reversible or not. And so the metrics here that we care about are kind of the number of kind of time steps required by the learner, as well as the number of reset interventions and the number of labels. And so here, the kind of goal of this problem statement is similar to the goal of SafeRL, which is to avoid unsafe states. While in our case, we want to avoid irreversible states, but essentially in SafeRL, they're able to kind of achieve this by assigning these unsafe states a reward penalty. And so in our work, we try to leverage these SafeRL algorithms as a tool for our problem by designating these irreversible states as unsafe in order to learn a policy that avoids them. However, SafeRL methods do require labels for every single visit state, which can be extremely costly in terms of supervision that's required, because as I mentioned earlier, in the worst case, these labels could come from a human supervisor if they can't be automated. And so this doesn't really help us design more autonomous agents. We're going to try to reduce this the supervision with a few optimizations. So the first one is to kind of query labels only at resets instead of every single time step. And so the result of this is that kind of these labels come, I guess, they're delayed. So instead of receiving them at every time step, we only receive them at the end of an episode when we ask for a reset. But given this kind of batch of labels, we can use a binary search strategy to reduce the number of required queries. Specifically, we know that all the states before a reversible state will be reversible, and all the states that follow an irreversible state are also irreversible. And so using this property, given a kind of trajectory of length t, we only need at most log t number of queries in order to kind of generate labels for every single time step of that trajectory. Next, to kind of determine when to terminate a trajectory and when to request a reset, we train a binary classifier on the labels to estimate each state's reversibility. And so this allows us to kind of use the predictions generated by the classifier as pseudo labels when kind of their ground truth labels aren't available. And then finally, we propose to kind of explore the environment a little bit after entering an irreversible state so that we can kind of collect more irreversible examples to make the classifier mentioned earlier a little bit more accurate. And so this exploration process is fully autonomous. And so there's basically no cost to it. And these additional examples, as well as we saw in our experiments, actually help improve the accuracy of the classifier quite a bit. And so to summarize our approach, essentially alternates between collecting new samples and training on them using the classifier's predictions as pseudo-labels. And then when the agent enters an irreversible state, at least as predicted by the classifier, the agent will explore for a few more steps, and then after that, request an intervention. And during this intervention, our algorithm queries labels for the states of that last trajectory. And then the environment is reset to initial state, and this entire process repeats. And this algorithm, we call it proactive agent interventions, or PAINT for short. Then in our experiments, we essentially took this existing benchmark called URL, and we kind of modified some of those tasks to introduce irreversible states. So for example, on the kind of the left two most tasks, where the agent can potentially drop the object off the table or push the object outside of its kind of like bounds of reach. And the agent in these tasks is given very infrequent resets. So for example, like a reset every 200,000 time steps, whereas each task only requires like around 100 time steps to solve. And essentially the agent has to decide when to request more resets to speed up learning. And so on the first two tasks, we found that PAINT, our method, requires only around 100 resets, which is almost 15 times fewer than prior methods. So kind of one of the comparisons that we selected was just SAC, soft Actor-Critic, but given resets at every 2,000 time steps. The other baselines include these kind of autonomous RL algorithms that implement these kind of forward and reset policies, but do not kind of explicitly consider irreversible states. Then on the non-episodic half-cheetah task, we find that PAINT is the only method that kind of achieves performance that's even close to the oracle. The oracle is in green here. And in terms of the number of labels, PAINT requires something on the order of like 100 times fewer labels than safe RL methods. So to summarize here, essentially we wanted to design robotic agents that can detect and can avoid irreversible states in order to learn more autonomously. And even though we had to provide these reversibility labels, which could be more costly in supervision, we found that they allow the agent to eventually on their own recognize these irreversible states and kind of automate this process. And so essentially, while a lot of these labels had to be provided at the beginning of training, we saw that towards the end, these resets were required less frequently. And so essentially, the supervision required also decreased over time. Great. So I wanted to summarize a little bit. So overall, in this talk, we've talked about 3 different ways that we can bring robotic systems a little bit closer to what I call continuous autonomy. So first, I introduced an algorithm to learn policies for new tasks more quickly by kind of reusing, reweighing the experiences from the previous tasks. Then we discussed non-stationarity and how to prepare for it through this unsupervised modeling of the latent task parameters. And finally, as we talked about, irreversible states can be a huge obstacle to continual autonomy since they require resets to allow the agent to kind of continue to resume learning. But through kind of efficient use of the reversibility labels, we can both detect and avoid these states by penalizing the reward. But these are only a few of the capabilities that are kind of required of continual learners. For example, after a policy has learned to solve a task, we would like it to remember how to perform this task, even after a lot of time has passed. And so earlier I discussed continual learning methods that prevent catastrophic forgetting, which is essentially what we like here. And even though I didn't delve into them deeply, it is definitely important to kind of continue making progress on this problem. This talk also covered how we can quickly adapt to changes that we've seen before. And from our experiments with LILAC, we also saw that they can extrapolate to some degree. But of course, more can be done to allow generalization to completely out of distribution changes. And of course, there are so many more capabilities that could improve the efficiency and the efficacy of these continual learners. And so maybe this is a good segue into my next slide, where I'd like to advertise a workshop that a few colleagues and I are co-organizing for this year's conference on robot learning. And so this workshop, we call it Robo Adopt for short. Essentially, in short, I wanted to advertise the submission deadline, which is November 1st. But if you're not submitting, we also encourage you to participate in the workshop, which is happening on December 15th. It is going to happen both on Zoom as well as in person in Auckland. But essentially, if you'd like to learn more about the topics that I covered in this talk, I think this workshop will be very relevant. And so please visit the workshop website if you want more details on that. And finally, I wanted to thank all of my collaborators involved in the different projects that were covered in this talk. I guess I'm happy to take them.
Thank you very much, Annie. Very interesting work. So I'll open the stage for question. You can simply unmute yourself or write it in the chat. See any icebreaker? Otherwise, I'll go with the first question. Yeah, someone was speaking.
No, it's fine. You can start first.
All right. I wanted to ask, how does, in the first part of your talk, when you were showing this lifelong learning and continuous adaptation, how does it compare to the other methods where you have more this meta learning or trying to look at this problem more at the hierarchical level, where you have some kind of, let's say, knowledge that is common to all the tasks, and then you have some parts that you fine tune for specific tasks?
Yeah, so actually in those experiments, we did not compare to, I guess, like more meta learning based approaches, just because as you can see, we are learning kind of over a sequence of like around a dozen, like 16 and 10 tasks. And generally, or at least like my expectation is that meta reinforcement learning based methods likely wouldn't perform very well on kind of such a like low task regime. where I guess my expectation is that like these methods kind of require significantly more tasks in order to kind of extract the information needed. And so I guess I do expect, like, as we see more and more tasks, so for example, towards the end, when we have like a sequence of like 10 tasks or 20 tasks, it makes a lot of sense to kind of apply meta-RL methods on this data set. Of course, it would have to be kind of some form of like offline meta reinforcement learning, since what we have access to here is the data set collected in these tasks, as opposed to kind of online access to every single task that we've seen so far.
Thank you.
So, hello, here's Behe Zarouki from the Technical University of Munich, and exactly from the Institute of Automotive Technology. I'm working also on continuous online reinforcement learning as well, combining it with online adaptive model predictive control. And thank you for the talk and for the presentation, and congratulations on your paper. One first question is the first part of your talk. Were you training only in one environment and then trying to transfer to the next? Did you consider, like, for the generalization, like to train on different, like multiple environments and then try to transfer to the next one? So there maybe it would be more general, and you can, with online learning, try just to close the gap to the nominal performance.
Yeah, actually, I think one of this could kind of be viewed in both ways, but one of like part of the motivation here is that we felt that like the sequential learning was more realistic, at least like more like physically feasible. So for example, if you consider these tasks that we were looking at, in order to kind of like train on multiple tasks at the same time, we'll have to like change the physical setup that like the robot is learning in for each different task. And so we felt that like essentially learning tasks sequentially actually is a more kind of realistic setup, at least for physical robots learning in the world. But of course, like this isn't always the case. For example, like mobile robots can like roam around, and so they could very well like go to like various parts of the world, and I guess like do this like sort of more multitask learning, where it kind of collects or it trains in various tasks, and so like round robin setup. Yeah, I guess like we were kind of thinking about like a very specific sort of setup where I guess like multitask learning kind of poses a challenge, because it's difficult to kind of like practically set things up in the real world in order to do multitask learning, if that makes sense.
Thank you. How do you measure success actually? How is success defined in the plots that you showed us?
Yeah, so I actually, it's a little bit different from in the simulations. We were kind of just measuring direct success by, so for example, in the valve rotation tasks, success was basically defined as like whether the final orientation of the valve was within some threshold of the goal. And then for the key insertion tasks, it was just whether the key was like in the hole or not. But for the kind of experiments we ran on the robot, it was a little bit harder to kind of to define, I guess, like a uniform metric for this. But for all of these, essentially, there was some kind of goal position that we wanted the robot to reach. And so we measured the distance to this goal. And that's what's reported in this plot.
Thank you.
Yeah.
All right. Last call for any further question. See, Gulyam, you can simply mute yourself and speak.
Okay, thank you. Can you hear me well?
Yeah.
Yeah.
First of all, thank you very much for your talk as well. I enjoyed it. I have a question regarding improvement with online data. How do you ensure that the collection and the use of the new online data make the overall performance better?
Yeah, this one, it's there is nothing very like explicitly that guarantees this. Specifically, like the initial policy that we used for this online phase was basically the pre-trained policy that we took from the offline phase. And so in some cases, especially in like cases where like the tasks were like what I'd say like extremely different or like adversarial, we did see that like this initial policy wasn't necessarily like very good for this particular task, especially when compared to, for example, starting with a random policy. But overall, we did find that like the online RL algorithm that we used, which was SAC, did kind of like do its intended job of like improving the policy performance as kind of more data was collected. And so in those cases, we did see that essentially like the kind of using this procedure was no better and sometimes even worse than learning from scratch because of the initialization of the online phase.
Okay, thank you.
Yeah, so the expectation is that hopefully there is like kind of some similarity between tasks and that like these kind of low level samples would be useful. But it would be nice to kind of have something a little bit more general where this like initialization is kind of guaranteed to be at least as good as like a random initialization of the policy.
Okay, thank you.
All right. So I think thank you very much again, Annie, for giving this talk.
Yeah, thank
And
you for having me.
we can see you all next week. Thank you. Bye-bye.